Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Josh Frieman, who is head of the Particle Physics Division at Fermilab, a Department of Energy national laboratory near Chicago that carries out fundamental research in high-energy physics. He is also professor of astronomy and astrophysics in the Kavli Institute for Cosmological Physics at the University of Chicago, and is currently president of the Aspen Center for Physics. He is a member of the American Academy of Arts and Sciences, an Honorary Fellow of the Royal Astronomical Society, a Fellow of the American Physical Society, and the American Association for the Advancement of Science. Welcome, Josh.
Thank you. It's a pleasure to be with you.
Yeah, thanks so much for being here. I want to start with sort of a general discussion on cosmology with a particular focus on your focus areas, dark matter and dark energy. To give you an idea where the audience could be, let me sort of reveal my own ignorance. At the risk of revealing my age, Josh, I have to say, when I was in engineering at Northwestern in the 80s, I was uncomfortable with what I did not know. But when I was in finance at the University of Chicago in the 90s, I was uncomfortable with what I knew. So now I am ready for physics, I think.
Okay, good.
So we know something happened 13.8 billion years ago. We don't know exactly what it is, and the universe was born. It was dense and hot, and over a long period of time, it expanded and cooled down. It was originally thought to be a sort of static universe, but by Einstein and others. But then Hubble, then at University of Chicago in the 20s, threw a wrench into that theory by finding that the galaxies are all running away from us. So the first problem was explaining the expanding universe. That intuition would have told us that the gravity of the stuff that we see in the universe would slow it down over time, the expansion, I mean, over time. So that was the expectation. But in 1998, you and others showed that the expansion of the universe is in fact accelerating, not slowing down. So now we have multiple problems, right? Could you provide a quick historical journey through these puzzles?
Sure, and that was an excellent summary, actually. But I do need to make one correction, which is I was not directly involved in the 1998 discovery, but we'll get to that.
Okay.
So yes, as you pointed out, Hubble and others established that the universe was expanding back in the 1920s. And I would say, in the decades following that, our picture of the expansion of the universe came together with this view that if the galaxies are all moving away from each other, you run that movie backward, the galaxies would all be approaching each other. And then we now know that 13.8 billion years ago, they would have all been on top of each other.
Right.
And that's an event we call the Big Bang. And that's really as far back as we can go with our current understanding of the laws of physics. And so we know a number of observations following Hubble's, particularly the discovery of the cosmic microwave background in the 1960s, this relic radiation of microwaves that fills the universe, that currently has a temperature of 3 degrees above absolute zero. That really solidified this picture of the universe starting with a Big Bang and then expanding outward from all points
So the
from
CMB,
that point.
so the CMB, Josh, the cosmic
Mhm.
microwave background. So this is sort of the baby picture of the universe, right?
That's right.
Something like 380,000 years after the Big Bang.
That's right. So exactly right. So in the very early universe, as you said, it was very hot and dense, which meant that the early universe was kind of a fog. Particles were interacting, scattering off of each other so frequently that they just couldn't go very far. They wouldn't travel great distances before they would hit another particle. And in particular, photons, particles of the microwave background of light, were interacting very rapidly with ordinary matter up until 380,000 years after the Big Bang. And then what happened is that by that time, the universe had become cool enough and diffuse enough that all these charged particles, say protons and electrons, started finding each other and combining to form neutral hydrogen atoms.
Yeah.
Once that happened, the photons were no longer frequently scattering. They could travel much more freely. In fact, they could essentially travel unimpeded from that point until today. So you're right. What that means is when we're looking at this cosmic microwave background radiation, we're seeing a picture of the universe as it was 380,000 years after the Big Bang.
So this
Sorry, I'm sorry. I need
Yeah.
to stop. I'm getting some weird system thing that says my system's going to reboot.
Oh, okay.
So
That's fine.
says updates were installed and the system needs to reboot in 5 minutes. I'm going to try to stop that from happening.
Okay, no worries.
But
Yeah.
I don't know if I can. If I drop off in 3 minutes, you'll
Yeah.
know why.
Okay.
Apologies for that.
No worries.
Yeah, but that's exactly right. The cosmic microwave background gives us this picture of the you said baby universe. I would have said adolescent universe, but nevertheless, the universe when it was much, much younger than it is today.
So the mechanics there is these photons escape when hydrogen atoms are formed, and they've been traveling 13.8 billion years or close to it, and they get redshifted all the way to the microwaves now, right?
Right.
That's what we are seeing.
Yes, exactly right. And so what we're seeing is, of course, when 380,000 years ago, the universe was much hotter. It was thousands of degrees. So that light was, as you said, had much higher energies, much shorter wavelengths, much higher frequencies.
Yeah.
But as the universe expands, the wavelength of light gets shifted from the blue or from high energy to the red or low energy. And so most of the photons in the microwave background today are in this microwave region, which we can which we can detect with radio telescopes. That's right.
So Hubble found things are kind of moving away from us. Einstein didn't really like that because he wanted the sort of the static picture. And so what did he do to kind of reconcile this?
So that's a good question. So I wouldn't say necessarily that Einstein wanted a static picture. It was rather that you have to remember when Einstein was coming up with his theory of gravity, general relativity. This is well before the work of Hubble. We didn't even know what the scale of the universe was. There was this big argument about whether these nebulae, these little blotchy clouds, were even things within our galaxy, or maybe they were distant other galaxies, what Immanuel Kant called island universes. And so basically, I think the conventional picture of that period when Einstein was working in the 19 teens was that the universe was our galaxy of stars. And if you just look at the stars in our galaxy, they're not moving away from us or moving towards, yet they're moving around,
Yeah.
but there's no net expansion or contraction of stars within our galaxy. And so it was reasonable to say, okay, the universe, the stars are just moving on these random orbits. Therefore, there's no overall expansion or contraction. Therefore, the universe is static. It's always been this way because there was really no evidence to the contrary. And so you're right. What happened was that shortly after inventing his theory of general relativity, which again is this new theory of gravity that replaced Newton's theory, which tells us that matter curves space-time and other masses and particles move in this curved space-time.
Yeah.
Einstein realized when he applied this, he and others actually applied this to cosmology, to trying to understand the universe as a whole, that it generally predicted that the universe would not be static. It would be dynamic. It would be, say, expanding or contracting. He knew that the stars in our galaxy were not all moving, rushing away from us or towards us. So he said, okay, there must be, my theory, doesn't predict a universe that we see. It predicts a dynamic universe. The evidence is that the universe, at least that we could see at that time before Hubble, was static. And so he introduced a new element into his theory called the cosmological constant.
Here's what I found.
Sorry.
No worries.
Sorry, that's my watch talking to me.
So I have a quick question. So
Yeah.
one confusion the general public has sometimes is that when we think about the expanding universe, it's really the fabric of space-time that's expanding. We won't really see it inside our galaxy. We don't see it, our solar system expanding.
Right.
It's all governed by gravity. So
That's right.
That is a confusion a little bit, right?
Yeah, no, that's a very good point, that we only see the expansion of the universe on scales larger than our galaxy or other galaxies. We didn't even know about really that there were other galaxies at that time. So we didn't know they were moving away from us. That was only discovered in the late 1920s by Hubble and others.
Yeah.
So it was reasonable to assume that the universe was static. Einstein and others found, though, when they applied the theory of general relativity to the universe as a whole, that it would be dynamic. It would be expanding or contracting. He at the time, now, of course, he later said this was his biggest blunder, or he's reputed to have said this is his biggest blunder, because of course he could have said, oh, my theory of the universe is expanding, and he would have predicted, Hubble's later discovery. It's not clear whether he really said that or not, but in any case, he didn't have the gumption to make that prediction, and instead he decided to introduce this new element into his theory of general relativity that he called the cosmological constant. And it's basically a new term which is new in the sense that so Einstein's theory of general relativity, when you make certain approximations, looks just like Newton's theory of gravity that we're all familiar with, that describes apples falling on your head and satellites going around the Earth. But this new term that Einstein introduced is something that's nowhere, it doesn't approximate to anything in Newton's theory of gravity. So in that sense, it's really new, and he thought of it as a new constant of nature.
He's
like
sort of trying to neutralize that expansion that was
exactly
emanating from the equation. Okay.
Exactly. So he introduced this new constant precisely so because he realized that this constant could kind of balance out the effects of gravity, in the sense that gravity is an attractive force, and so it would tend to make the universe contract. You need something that would sort of counteract that if you want to have a universe that isn't contracting or expanding, that's just stable, it's just static. And so he introduced this constant that would be a kind of counter force to the attractive force of gravity. And he showed correctly that you could get a universe which is static, which isn't expanding or contracting, if you have this constant and it has the correct value. And that value turns out to be so small that we wouldn't have observed its effects on the scale of stars in our galaxy. And so it was sort of a safe thing for him to have introduced. And the interesting thing was what Einstein didn't realize was that these solutions, these static universe solutions to his theory with a cosmological constant, were unstable. So if you perturb the universe just slightly from this Einstein static universe, it's called, then it would either contract or expand. And so you really wouldn't expect the universe after billions of years to still be in this static state. It would be expanding or contracting. And so in a sense, he, and of course, Hubble later discovered that the universe was expanding. And once that happened, Einstein said, oh, that was the biggest mistake I ever made. I should never have introduced this term. And of course, others then pointed out that it didn't even do what he really wanted it to do anyway. But
so that's a lambda. That's conventionally called the lambda, or
it's conventionally called lambda. Yeah.
Okay. And so when Hubble's data came forward, did he keep it there in the equation, or did he just set it to zero, or just take it out completely?
Well, so it was interesting. I think at that time, Einstein's view, I believe, was just, okay, Hubble's found that the universe is expanding. There's no rationale for introducing this constant. And so, yes, we should just set it to zero. And the interesting thing is, I think if you look at sort of cosmology in the 20th century, lambda, this term, sort of had a very bizarre history in the sense that Einstein originally introduced it for the wrong reasons.
Yeah.
And then he said, okay, let's get rid of it. But then others, periodically, there would be a new kind of observation in cosmology which didn't quite fit. And people would sort of drag the cosmological constant out of the closet and say, oh, we can explain this new observation if we introduce a cosmological constant, not necessarily to get a static solution, but to get some kind of solution that fits this particular data set.
So it was always,
yeah, go ahead.
No, it was always waiting as sort of a crutch that you can introduce.
Exactly, it was a crutch. And then a few years later, people would realize that this new data set they were trying to explain was wrong. And so they would stuff the cosmological constant back into the closet and say, okay, sorry, we didn't mean that. That was a mistake. And then a few years later, some other new observation would come out and they would again pull the crutch out of the closet. And again, a few years later, stuff it back in. And I think people, so it sort of got a weird reputation as this, it's sort of something you're not very proud of.
That never dies. That never
dies. Yeah. And I think really what changed, though, is realizations actually from people studying the physics of elementary particles, at some point realizing that, wait a minute, you can't just stuff this thing back in the closet. And that, in fact, in quantum theory, you can actually predict, calculate what the value of the cosmological constant should be. Because in quantum theory, the cosmological constant gets reinterpreted. It's not this constant of nature that you can choose set to some arbitrary value, which is what Einstein's view was. Instead, it was really realized that this, and this actually realization came early on, but it sort of took years to really gain acceptance, I think. But what physicists realized is you could reinterpret this not as a new constant of nature, but in fact as the energy of empty space itself.
There was another puzzle, which is the universe is extremely uniform and isotropic, and so it needed, from the Big Bang perspective, it needed something else, right? It needed inflation to sort of explain it.
Right.
And so how does that change the view of lambda, if at all?
Yeah, so that's a good point. So in essence, that's in a way a continuation of this story, which is it was realized that lambda was associated with the energy of empty space, or the energy of the vacuum.
Yeah.
And it was also realized that that energy can change. And it can change just when the universe undergoes certain sort of phase changes, what we call a phase transition. So just like you go through a phase transition from, say, water to ice as you cool it, we believe now from the physics of elementary particles that as the universe expanded and cooled, it actually went through a series of these phase transitions. And when that happens, you can show that this energy of the vacuum of empty space should change, and in fact, it can change by a very large amount.
Yeah.
And this vacuum energy was recognized by Alan Guth and others around 1980, that you could have a kind of phase transition where the universe would, it's what he called it supercooling. So you can get a situation where you cool water down, but because of external circumstances, it doesn't immediately change to ice. It sort of stays in this supercooled liquid state. And Alan Guth realized that in theories of elementary particle, the same thing can happen to the universe. And if that did, then what would happen is that this lambda, this vacuum energy associated with this phase transition, would become dominant and would drive the universe to expand extremely rapidly, in fact, exponentially. So just the opposite of what Einstein had introduced lambda to do. Instead of making it static, it would drive this extremely rapid expansion, which Alan Guth called inflation. This would happen, in his theory, a tiny fraction of a second after the Big Bang. And if that period of very rapid expansion lasts long enough, it can effectively explain a lot of the large-scale features of the universe that we observe, as you mentioned. The fact that it appears isotropic, it looks the same in different directions. It looks homogeneous, that is, it looks like it has the same properties over here as it does over there. And in fact, we now believe that that period of inflation is also what produced all of the structure that we now see in the universe through the effects of quantum mechanics.
So mechanistically, Josh, so what stops that inflationary phase? Is the lambda changing as that inflation happens?
Yeah, that's a good question. So so the answer is that in this, it's again, we don't know exactly, because we don't know what the correct theory of inflation is.
Yeah.
But again, it's the idea is essentially that this phase transition eventually does go to completion. So if you supercool a liquid for long enough, eventually it turns into ice. And so that's the idea, is that eventually the physics of this transition goes to completion, and the universe, and when that happens, this lambda, this energy of the vacuum, goes away. It's really a transitory property. It's a property of this supercooled state, which then disappears. So it's not a true constant of nature the way Einstein thought of it.
So that is still sort of being explored, but I think that is the accepted idea, inflation, right? And then
I think I think it's I would say it's, it fits all the observations very well. So it's certainly a working hypothesis of most cosmologists, not all, but most.
Right. Yeah, I know that there's some experiments going on in Chile and the South Pole to look at the polarization and so on to fully confirm it. But it seems like a large number of cosmologists accept that. And then we have this 1998 problem,
right?
Which is it was based on the supernova discovery.
Right. Right. So that gets right. So what we were just talking about with inflation, you can think of it as a period when there was something like a cosmological constant, but very, very early in cosmic history, tiny fraction of a second after the Big Bang. Inflation ends. We go, we transition to a normal universe, so-called normal, which has basically matter and radiation, so photons and others. You go through this period that we already talked about, 380,000 years after the Big Bang, when suddenly the photons get freed and they stream towards us freely. And then the assumption had been that as the universe continued to expand and get more dilute, the dominant force on large scales was gravitation, which would make the universe, the expansion, gradually slow down, right? The galaxies over on this part of the sky are moving away from the galaxies over in this other part of the sky, but gravity is still tugging between them, so you
Yeah.
expect them to gradually slow down relative to each other. But what was discovered in 1998, and there were definitely hints earlier for something like this going back to really the early 1990s, but the definitive data sets was in 1998, and this was two teams of astronomers studying supernovae. These are stars that once they run through their lifetime explode. They become very bright over the course of 2 weeks. A star that was, maybe comparable in brightness to a standard star or less, suddenly became as bright as an entire galaxy of billions of stars. And what was done in the late 1990s is these two teams realized that they could actually systematically discover these supernovae rather than having to just wait for one to go off by chance. They could actually set up a program where they knew they would discover supernovae, and that was something relatively new.
Yeah.
That supernovae are very rare. They go off about once per century in a typical galaxy. So you don't just look at a single galaxy for 100 years. That's too long. But if
Yeah.
you realize, if you look at a gazillion galaxies over the course of a number of nights, then just by chance you will see a number of these supernovae. And if you have a big telescope that can see distant galaxies, then you will see supernovae that are very far away.
Yeah.
And so that's what they did. These two teams really were the first to kind of have these programs where they were guaranteed to discover quite distant supernovae. And what they each discovered a few tens of supernovae that were very far away, and they found that those supernovae were about 25% fainter than they expected them to be, based on previous observations of more nearby supernovae.
Yeah.
And this was really the evidence that faintness of those distant supernovae relative to what we expected was this evidence that that the expansion was speeding up. It was not slowing down to gravity, but it was speeding up due to something which we now call dark energy.
So that brightness, Josh, is there something, something standard about that
Right.
brightness? So what is the mechanism there?
Sure. Good. Yeah. Good question. So you're right. There's a particular kind of supernova that they were focused on called a type 1A supernova. It's just a particular, we classify supernovae based on certain observable features in the spectrum of their light. And the type 1A supernovae had been found to be, as you suggested, nearly standard candles, which what that means is, think of light bulbs, and you have probably a bunch of different kinds of light bulbs in your house.
Yeah.
But you could imagine, some of them may be 25 watts, some of them may be 50 watts, some of them may be 100 watts. But suppose you decided, okay, all I want is 100-watt light bulbs. And so every light that you put in your house, suppose you put only 100-watt light bulbs in. Well, then if you know that all your bulbs have the same brightness, then by looking at each bulb and seeing how bright it appears to you, you can tell how far away it is. The lamps that are closer to you look
Yeah.
brighter than the ones farther away. And if they're all 100-watt bulbs, you can actually, by detecting how much light you're getting from the nearby lamp versus the more distant one, you can tell the relative distance that they are away from you. So it's called
So,
standard candle, and that's the technique that was used. It turns out these type 1a supernovae, they are, we think, the explosions of white dwarf stars.
mhm.
And we believe, for a number of reasons, and have evidence to believe, that these white dwarf stars, when they, about 2.5 weeks after they explode, are all very similar to each other in brightness. They're all not exactly the same wattage. That wattage varies up and down by maybe 10, 20%, but that's good enough to use them to map out the expansion.
So you see a supernova at some galaxy. You already have a distance measure to that galaxy by some other means,
No, so
or
it's
no?
precisely the brightness of that supernova that
Okay.
tells you the distance. And then the other piece of information you have is you measure the spectrum of light from, say, all the stars in that galaxy.
Yeah.
That tells you what we call the redshift, which is essentially how fast that galaxy is moving away from us due to the expansion of the universe. So if you have both the redshift or the recession speed from the spectrum, and then you have the distance from the brightness of the supernova, then by looking at the ratio of essentially the recession speed to the distance for a
Yeah.
number of different galaxies at different distances from us, that allows you to map out this cosmic expansion history, we call it. It's basically how
Okay.
fast the universe has been expanding at different points in time as we go out in space and therefore back in time.
And so we found those things are moving away, not just moving away, but moving away at a faster rate against time. So the universe is accelerating its
Right.
expansion.
That's right.
And so that doesn't quite fit with sort of the standard theory then. So you had to introduce something to try to explain this.
Right, exactly. So just the way Einstein introduced the cosmological constant to get a static universe, it was already well known that if the universe was speeding up, was accelerating and not slowing down due to gravity, that a way to do this would be to again pull the cosmological constant out of the closet, as we did many
Okay.
times and through the 20th century, stick it back into the equations, and again, if you gave it the right value, it would tell you that the universe, starting about 7 billion years ago, went from slowing down to speeding up. And so the initial, I would say, interpretation, or the simplest interpretation of what the supernova data were telling us, was that in fact, we had to pull Einstein's cosmological constant out of the closet yet again. And that was part of the reason, I think, why initially there was quite a bit of skepticism in the late 90s from some quarters, people saying, oh, this is that same old story. They're pulling it out of the closet again to explain this later data set. It's just all going to go away, and then the astronomers will stuff it back in the closet.
Yeah, but this time it has sort of a physical meaning to it.
Well, I think it has the same meaning.
Yeah.
I mean, as I was saying before, our physical interpretation of the cosmological constant did change in the intervening period,
Yeah.
in terms of, instead of thinking of it necessarily as a constant of nature, thinking of it as the energy of space itself. And as I mentioned, physicists in the meantime had thought more about how to calculate what that energy of empty space should be. So you can imagine a thought experiment. I have a bottle of water on my desk. I could imagine, sealing this bottle, hooking a hose to it, a vacuum hose, sucking all the air molecules out of this bottle, And so suppose I did that in a way that the bottle was just completely empty of molecules. It had only empty space in it. Now, in classical physics, you can calculate what the energy of the empty space in that bottle is, and it's zero. There's no particles, so there's no energy. In quantum physics, and this was actually recognized early on by Wolfgang Pauli and others, you can calculate what that energy of empty space is in quantum mechanics, and it's not zero. And unfortunately, the answer you get is infinity. And we know that's not the right answer. There's not an infinite amount of vacuum energy in this water bottle here. So the point is, we knew that we knew that there was, a physical way to describe this vacuum energy, but we still, as of yet, don't have a consistent way to calculate it. But still,
And
that
that's
physical, the point is, though, that because we think it has this physical interpretation, physicists eventually realize that, we can't just keep pulling this thing out of the closet and stuffing it back in. It's something that, in principle, we should be able to calculate. We get infinity. We know that's the wrong answer, but that doesn't tell us that the correct answer is zero. The correct answer, if we are smart enough, may be something that's non-zero that we haven't yet figured out how to calculate. And I should say that, people over time tried to fix up that calculation, but even if you try to fix it up, you still get an answer which is over, in some cases, over 100 orders of magnitude larger than what we know it to be. And I like to say that it's really hard to make a math error that big. If you're doing a calculation, or you enter some numbers in your calculator, maybe you enter the wrong digit and you're off by a factor of 2 or 5 or even 10 or 100. But to be off by a factor of 10 to the power of 120, you really have to work hard to make a
right.
mistake that big. So that's telling us that there's something fundamental that we're not understanding.
So that vacuum energy is one of the candidates, just one of the candidates for this observed accelerated expansion of the
Yeah.
universe, right? So I'm wondering, George. So since we know what the expansion rate is, we could actually back compute what that number has to be for this to work, right?
Yeah, that's right. So we know actually now quite precisely that if what we now call generically dark energy, if the correct model of dark energy is this energy of empty space, the vacuum energy, again, which is equivalent to the cosmological constant, then we know rather now just in the last few years quite precisely how much of that energy there needs to be. And it's about 70% of the total amount of energy in the universe. The other 30% is made up of dark matter and of ordinary matter. So we know that number now with quite a bit of precision compared to even 5-10 years ago.
Okay, so 70% of the universe has to be what is called dark
Right.
energy. If I understand this correctly, George, the vacuum energy is just one of the candidates for it, right? There
Exactly.
could be other potential candidates in the
Yep.
future.
Or now. Yeah,
And
there are other
or not.
theories for what that could be. So dark energy is the generic name. Vacuum
Yeah.
energy is one possible instantiation of dark energy, but there are others.
And do I understand this correctly that one of its properties, which is very counterintuitive, one of its properties is that it keeps increasing as the universe expands. So this is sort of a runaway expansion process, isn't it? If that is true.
Yeah, so if dark energy is the energy of empty space or vacuum energy, then it means that we're living at this interesting time when it makes up 70% of the universe, and I said other forms of matter make up 30%. But then as you run the universe movie forward, the other kinds of matter in the universe, including us, become more and more dilute.
Mm.
But vacuum energy has this strange property that as the universe expands, it doesn't become more dilute. The density of dark energy or vacuum energy doesn't change as the universe expands, which means that as you go forward in time, billions of years into the future, that 70% number, becomes 90, 99, 99.9999%. And eventually
Mm.
the universe will just be empty and just dark energy. Um, uh, and it will be expanding exponentially fast, much like it did, we think, during this primordial epoch of inflation. Now, I shouldn't say it would be
Oh, that's
completely empty. We think that actually, so this is a sort of an interesting side bit, but
yeah,
when we hopefully we'll talk a bit about surveys, cosmic surveys
yeah,
to probe these things. Today, we can see billions of galaxies in our cosmic surveys
mm,
and chart them over the sky. In the far distant future, tens of billions of years from now, all those galaxies will have receded away from us due to the accelerating expansion of the universe. And we think
yeah,
we will only see a handful of nearby galaxies that happen to be gravitationally bound to our Milky Way galaxy or to our neighbor, the Andromeda galaxy. And what's
mm.
interesting about that is that would then return us to Einstein's static universe. We would, as far, suppose in billions of years in the future, they forgot about dark energy and all that stuff. They
Right.
start anew looking at what they can see in the universe, and they would see, oh, there's a handful of nearby galaxies, and that's it. And they would not discover the expansion of the universe because there would be none of these other galaxies moving away from us that would still be visible. So we're,
So,
we're,
so future Einstein gets his equation again, puts lambda in there, but there is no Hubble
that's
this
right.
time.
That's right. Yeah. So I like to say that because of this is why we need to fund astronomy now while we can still see all those galaxies because we only have maybe 10
Right,
billion years to be able to see them before they'll disappear over the horizon. So
right. Let's get to it. So we have this one other issue, which is we look at the rotations of stars around the
mhm.
galaxy. Um, we can't quite explain that, right? So we have to make up another dark
Right.
thing to sort of complete the story.
Exactly. So that's what led to that leads to the notion of what we call dark matter, which is different from dark energy. Dark energy we think is this stuff which is causing the universe to speed up, the expansion to speed up. Dark matter is something which holds galaxies together. And again, this was the first inklings of this really came in the 1930s. A Swiss astronomer working in California's Fritz Zwicky noticed that the galaxies within a particular cluster of galaxies called the Coma cluster were zipping around very quickly, more quickly than they should have been, given what he knew about the masses of those galaxies and their gravitational attraction. Then in the 1970s and 80s, Vera Rubin and her collaborators studied, as you noted, they studied the orbits of stars and gas within galaxies. So spiral galaxies like our Milky Way are rotating around their center, and they could measure the speed of rotation of stars as a function of their distance from the center of a galaxy. And they realized that these stars were zipping around these galaxies much more rapidly than they should have been, given the mass that they could tell was in the stars in those galaxies. And so those stars moving so quickly should have just been zipping out into empty space. It didn't appear that there would be enough mass inside the galaxy to hold them into those orbits. Um,
Yeah.
and the analogy you can use is think of planets in our solar system going around the sun. And as the further out you go, so as you go to, whatever, Jupiter, Saturn, Neptune, Neptune,
Yeah.
Uranus, the further out you go, the orbital speeds of the planets get less and less, and that's simply because the gravity of the sun is weaker the farther out you go. And so those orbitals, the equivalent of a year or the time it takes them to do their orbits is getting longer, partly because they're just farther out and they have longer to go, but also because they're just moving more slowly than the inner planets are. And that's what we
Right.
would have expected when we look at the stars in the outskirts of galaxies, that most of the mass is contained in the stars in the inner part of the galaxy. So the stars way out there circulating, their orbits take 100 million years or more, but still we would have expected them to be moving more slowly than the stars closer to the center of those galaxies. And in fact,
So
what
there's,
Rubin
yeah.
and her collaborators found is that they were moving roughly at the same speed at very far distances as the inner stars. And therefore, there must be some additional mass, which we can't see, holding those stars into those orbits. And that's what we call dark matter.
So if I understand this correctly, George, there are two issues, right? One is those things in the periphery are moving too fast, and the other is, given the current theory, if they're moving that fast, they will just they won't be able to stay
That's
there.
right.
Both of those
Right.
issues, right?
So there must be, we posit that there's something additional in addition to all the stars and gas we can see in those galaxies. We posit there must be some additional matter. We're not seeing it in our telescopes, and so that's why we call it dark matter. It has to be something which doesn't shine, it doesn't interact with light. Otherwise, we would have detected it through our telescopes.
So if you call it dark matter, it's really transparent, right? Because it just doesn't interact with anything. Light will, all frequencies will go through
Yeah,
it.
yeah.
Is the intuition? I don't think it works, but is it sort of all the stars are floating in some kind of viscous fluid type thing or not?
Not necessarily, because again,
Yeah.
well, we don't know what dark matter is, but our best, well, first of all, we know what it's not. So we know
Yeah.
it's
Right.
not made of ordinary matter. The stuff. So you and I are fundamentally, we're made of, we have molecules made of atoms. The atoms have, nuclei and electrons spinning around the nuclei are made of protons and neutrons. Those protons and neutrons are made of quarks. And
Yeah.
and we know that the dark matter is not made of anything like that. It's not made of quarks. It's not made of electrons, because we know from other measurements how many quarks or atoms there are in the universe, and there just aren't enough. So we think
Right.
our best guess is that the dark matter is some new kind of elementary particle, but that simply doesn't interact very strongly with the particles that we know and are made of. So these are sort of a standard candidate for dark matter is what are called weakly interacting massive particles, or WIMPs.
Yeah.
That's not the only candidate, but that's a popular class of candidates. So these are particles that could be perhaps as heavy as a proton, perhaps 10 to 100 to 1,000 times heavier, or perhaps much lighter than a proton. But unlike the proton or the neutron or quarks, they don't interact with the particles that we're made of, or that our detectors are made of, at least
Yeah.
not very strongly.
Right. Right. And so I know that there were some other like primordial black holes and other ideas around this, but the status quo today is we sort of know the distribution of this thing, but we don't know what it is.
Exactly right. Yeah,
Right?
we know where the dark matter is. We know how much of it there is in the universe. It's about 25%. We can measure quite accurately now its distribution in galaxies and clusters of galaxies. But you're right, we don't have a clue of what it's made of. It could be these WIMPs, it could be primordial black holes. We don't even know the mass of these things, whether it's tiny, tiny microscopic or something of the scale of a planet or even a star. So our ignorance is vast. There are a lot of experiments trying to look for this, and so far we haven't found it.
And so we believe it's about 25% of the total universe. So we have sort of a 70, 25, 5
That's right.
split
Right.
today.
So the 5 is the stuff we're made of.
The 5 is the stuff that we
Right.
can see. The other 2 components we
Right.
cannot, and we don't know really
Yep.
what they are. And when we sort of move the movie back to time equal to 0, the split changes, right? So very close to time equal to 0, dark energy was close to 0. Is that
Well,
right?
relative to the other components, that's
Okay.
yeah. In most models, it was negligible at early times. That's right.
And dark matter was dominating, and we believe as we go forward, dark energy will dominate.
Right.
So that runaway expansion, Josh, will that necessarily lead to sort of the big rip scenario for the end of the universe?
Well, that depends on what the dark energy is. So if the dark energy is this energy of empty space or the vacuum energy that we were talking about, that doesn't lead to a big rip. It just leads to this continued exponential expansion of the universe, but it won't literally rip things apart. On the other hand, there are scenarios or models where dark energy could have the property that, so I mentioned before that as the universe expands, ordinary matter and dark matter become more dilute, but vacuum energy just stays the same. It doesn't become more dilute as the universe expands. But there are these models where, in fact, very bizarre, I mean, it's bizarre enough that as the universe expands, vacuum energy doesn't get more dilute. But you can come up with models where not only does it not get more dilute, it actually becomes more dense as the universe expands. And in that case, the sort of sped up expansion of the universe itself speeds up in a way. And what that means is you not only have exponential expansion, but you have sort of super exponential expansion to the point where not only will all those billions of galaxies disappear over the horizon, but even those handful of galaxies that we thought were gravitationally bound to our Milky Way, they will get ripped out of orbit. And then the galaxies themselves will get pulled apart. And in fact, eventually, stars, the Earth, atoms themselves will get pulled apart. And that's what you're referring to with the big rip. Now, again, that's, I would say, an unconventional model for dark energy, but it's still a possible model for what the dark energy could be.
Okay. You are in the midst of a very interesting experiment, dark energy survey. I guess it has been going on for 2-3 years now, and the first data has come in. You want to talk a bit about the design of it, but what expectations?
Yeah, so the dark energy survey actually started taking data, started surveying in 2013 and finished last year, and we're now analyzing the data. So this was a survey that we designed in the early 2000s, really meant to, shortly after the discovery of cosmic acceleration from the supernovae that we talked about. And it was realized at that time that what we really wanted to do, the supernova results were very exciting. We knew the expansion was speeding up, but we realized that to make progress, is it the energy of empty space? Is it this big rip? Is it some other form of dark energy? We realized that we really just needed much more data to address those questions. And so we designed this survey to basically make a map of as many galaxies as we could over a short period of time. And so the dark energy survey is just a large digital camera with about 570 million pixels. So it's about the size of, I don't know, sort of in width, it's maybe like a wine barrel, but probably twice as long as a wine barrel, and
Yeah.
built it over the course of about a decade. It was placed on a telescope in Chile called the Blanco telescope, which has a mirror that's 4 meters across. So it's a good size telescope. And over 5 years, we took snapshots, basically images, over about
Yeah.
1/8 of the sky that you could see from the Earth. And that gave us a
Well, yeah.
map of about 400 million galaxies, give or take.
This will be I would imagine, the largest survey ever, right? Given
It's the
that scale.
largest survey, yes, I would say, yes. It's the largest survey of that type, certainly, because
Yeah. Yeah.
it goes, this camera on this telescope has two features. One is it's a very big camera, so it can look at a large swath of the sky at once. But it's also
Mm.
very sensitive, and it's on a large telescope, so we can also look very deep. There are cameras that are on bigger telescopes, but they can see smaller parts of the sky. There are cameras on smaller telescopes which can see more of the sky, but they can't go as deep. And so we were aiming for this sweet spot of covering about 1/8 of the sky, but going very deep, so that we could map out these hundreds of millions of galaxies to try to really do two things. One is to map out this history of cosmic expansion much better than they were able to do in 1998, so that we could
Mm.
really precisely measure how the expansion rate has changed over time. And the other thing we're doing with this data is studying how the history of structure of the universe. So early on, we talked about this picture of the cosmic microwave background 380,000 years after the Big Bang. That tells us that at that early time, the universe was very smooth. There were tiny little ripples in the density or the temperature of the universe, but they were really, really tiny. But due to gravity,
Yeah.
those small amplitude fluctuations became magnified and grew to all the structure we see in the universe today. And so we
Right.
realized that by making this kind of survey, we could measure the amount of structure in the universe over cosmic time. And because
Mm.
the growth of structure as well as the expansion rate reflects this cosmic tug of war between dark energy and gravity, we wanted to have both of these kinds of measurements to really be able to map out that cosmic tug of war over 8-10 billion years.
So, so you're not really. It's not longitudinal data, right? I mean, it's too short a time
That's
frame to
right.
even see it. So, is it the
Yeah,
redshift?
exactly.
Well, how do
So
you?
what we
Yeah.
do is we have this camera, and we use different filters on this camera. So on a given exposure, we'll put a red filter through it. And then we'll
Mm.
replace the red filter with a blue filter or with a green filter or with a very nearly infrared filter. And so each part of the sky, we can map out, we can not only see the galaxies, but we can determine their colors. And,
Yeah.
we talked about the redshift. So a galaxy further away from us, moving faster away from us due to the expansion of the universe, will look redder. That's the origin of the term redshift, than one that's nearby and moving away from us more slowly. And so by measuring the colors of these hundreds of millions of galaxies, we can tell roughly how far away each of them is, and we can we can make a map that's quasi three-dimensional. So not only where they are on the sky, but roughly how far away they are. And so we can look at the amount of lumpiness or in the spatial distribution of those galaxies back in time or through these slices of distance using the colors of the galaxies.
Do you expect some sort of a predictable pattern?
Yes. Yeah.
Of okay.
So exactly. So that's the other thing that's happened that's been quite remarkable in cosmology is there was the discovery of cosmic acceleration, but also, we talked earlier about the cosmic microwave background. When that was first discovered in the 1960s, as I mentioned, it looked the same in all directions. The temperature was 3 degrees over there, 3 degrees over here, and it just looked like this uniform, what we call isothermal, just single temperature system. But starting in the 1990s with the COBE satellite, then a number of ground-based experiments, most recently the Planck satellite, we've now mapped out very fine differences in the temperature and, as you mentioned, the polarization of the cosmic microwave background with extreme precision. And that's enabled us to make a very precise model for structure in the universe at those very early times, 380,000 years after the Big Bang. So that gives us a real precise snapshot of structure at that time. And then we can say, okay, we know what's happened since then is gravity has amplified those fluctuations. So with the cosmic microwave background, we can make a prediction for what the patterns of galaxies on the sky should look like today, statistically. We can then go out and measure those patterns, compare them to the predictions of the theory, and that's what enables us to measure things like, okay, how much dark energy is there in the universe, how much matter is there, and what's the history of structure and of the expansion rate. So we have this comparison of what I would call late universe measurements from the Dark Energy Survey and other surveys to the early universe measurements from the cosmic microwave background. First of all, the fact that they agree at all is remarkable, because you're extrapolating over billions of years. But through that comparison, we learn a lot about, and we hope to learn much more about how much dark energy there is and what its nature is.
Yeah, it's not really the spatial specific kind of matching, right? It's just the aggregate expectations.
That's right. So these are all what you would call statistical measurements. So for example, one way to think of this is if I have a galaxy at a certain location in space, the theory predicts what's the probability of finding another galaxy within a certain distance of that galaxy. And then what's the probability of finding a third galaxy within some other distance? And so the theory makes predictions of that type, these sort of probability statements about the spatial distribution of galaxies and also the spatial distribution more generally of matter, including dark matter. And so we compare the theory on that kind of probabilistic basis.
Okay. Yeah, you have something. So this has been going on from 2013. Now you're into the data analysis phase. You had a paper just came out this month on it. So what is sort of the early findings? From the data?
I think what this recent paper did was, in fact, made the kinds of measurements we were just talking about, these sort of probability measurements of, if I have a galaxy here, what's the probability of finding another galaxy, say, within 2 million light years of that galaxy? And so it turns out we can make many such measurements of that type. So, for example, we can look at, say, pairs of galaxies in that way and just look at all pairs of all galaxies over the sky. That's one measurement we can do. But there are other measurements we can combine that with. For example, suppose I have a galaxy that's, a billion light years away, and another galaxy behind it that's 2 billion light years away. Well, because of the gravity of that galaxy, the foreground galaxy, that's going to distort the apparent shape of that distant galaxy because the light from that distant galaxy passes near the foreground galaxy on its way to us. It's passing through this curved space-time, and that leads to a what we call a shear or a lensing effect of this distant galaxy, which we can again measure statistically. So we can, in addition to measuring, say, what's the probability of finding two galaxies a certain distance apart, we can also say, I have a galaxy that looks like it's sheared by this amount. How does that correlate with the shear of this other galaxy nearby it on the sky? So that's another probabilistic measurement we can make. And we can also say, what's the relationship between the shear, the shape of that background galaxy and the position of the foreground galaxies that I can see? That's another probabilistic statement. And so what we've been doing, and what this paper does, is it basically says, let's look at all the kinds of probability measurements we can make like that, involving what we call 2-point correlations, where you've got a galaxy in a galaxy, or a galaxy in the shape of another galaxy, or the shape of this galaxy in the shape of that galaxy. And it turns out that by those sorts of measurements give you complementary information. And there's now really a whole industry of making those measurements and then finding the ways to properly combine the information from those 2-point correlation functions together to really constrain cosmology. And so what this paper was doing was, I think, kind of the state of the art for combining. I think we ended up with 6 of those different measurements that we combined together. And that gives you, in that paper, we were looking at constraining the density of matter in the universe, mostly dark matter, and the current lumpiness of the universe, or the amount of structure we see. And
constraining meaning kind of put a bound on it,
right.
min and max.
And the reason that's interesting is because, again, as I said, we're using these measurements. They're sort of telling us about the lumpiness of the universe today. We can compare that to the cosmic microwave background measurements, which again, are looking at the universe much, much earlier, where it was much less lumpy, but which you can extrapolate to how lumpy the universe should look today. And there's a question of whether they agree with each other or not. And there's been quite a bit of, I would say, controversy about whether our measurements on the clumpiness and the density of the universe really agree with what we're seeing from the cosmic microwave background. And I think, I would say that the answer currently depends on who you talk to. Some people will say there's kind of what we call a tension between those measurements. Other people would say, no, look, they look consistent with each other. And I think the real answer will come when we analyze more of our data. The paper that came out recently was still using a very small fraction, I think less than 20% of our data. We have much more data, so-called in the can, that we're analyzing now. And so our constraints on the lumpiness and the density will get quite a bit stronger, and either it will start to agree better with the cosmic microwave background or it won't. If it doesn't agree, then you say, okay, the theoretical construct I was using to compare these two was a model that, for example, dark energy was this vacuum energy or a cosmological constant. So maybe we need, if they're really not agreeing, maybe that's suggesting, the dark energy is something different, or it could even involve some other, perhaps neutrinos. If I change the mass of neutrinos, these very light particles, that can affect this comparison. So I think we're going to learn a lot in the next few months when our next results come out, and then in the next couple of years when our final results come out, whether this tension is really significant and it's pointing to some what we would call new physics, or whether everything looks perfectly consistent with the sort of simplest model of dark energy. And of course, there are other surveys coming after ours, which will attain even greater precision.
So this is sort of a scenario analysis tool now, right? So you can go in and set certain features and see whether you're getting a better
Yeah,
fit,
I mean,
so to speak.
if you like, what we typically do is say, let's assume what we would call a vanilla model, sort of the model with, the fewest number of knobs or dials or model parameters. And
Yeah,
you always start with simplicity, and you see if that works. And if it does, then you say, okay, at least this is a consistent model. It doesn't mean it's the right model. If it doesn't seem to fit, then you say, okay, maybe I don't have the right physical model. I add in more parameters, say the mass of a neutrino, the properties of the dark energy. That complicates the model. Uh,
mm,
Generally, that will give you a better agreement between the model and the data, just because you've introduced more freedom into the model. And then you have, statistical questions, you can answer, which you can address, say, with Bayesian methods of statistics about, all right, is the agreement so much better between the model and the data that it
right.
justifies having made a more complicated model? And those are things that you can quantify in the context of, say, a Bayesian statistical analysis.
So you have a baby picture. You have a picture when the kid is 15 years old, and you're asking, can we actually predict where the kid grew up
Right,
and
and what
what
old
what
person they
what
grow
he or she
into.
ate and
Yes,
so
right. Yeah.
on. Okay. So in conclusion, then, Josh, if you look forward 5 years, we have come a long way. It seems like a lot of the data is fitting, but there are still a lot of questions. So what is your expectation 5 years, 10 years from now?
Hmm.
From a theoretical perspective, and technology is
Right.
improving, so perhaps we'll get better measurements as well. So what's your overall expectation, say, five,
Yeah,
ten
that's
years
a
in the
good
future?
question. Well, we will certainly have more data and better data. As I said, our survey, we finished data taking. We're analyzing it for the next couple of years, but there are already new surveys that some starting now. There's one called DESI, which is a big survey using a very similar telescope, but that's in Arizona. There's a new telescope being built down in Chile called the Vera Rubin Observatory, which will do a survey much like ours, but it's a much bigger camera, much bigger telescope, and they're going to have 10 full years to do the survey, whereas we had, a fraction of 5 years. So the
Yeah,
data over the next 5, 10 years
yeah,
is just going to become, I mean, it's already a lot of data now, but it's just going to become staggering. So the challenge is going to be getting our methods of analyzing the data to keep pace with these technological advances, which are just giving us so much more data. As you
mm,
acquire more data, your treatment of it needs to become much more careful, because any little error or uncertainty can give you a wrong answer. And when you have very little data,
yeah,
those uncertainties can be masked because just your statistical errors are so much larger. But when you have such large data
mm,
sets, our ability to model every little detail becomes much more important. And so that's the concern I have is, are people analyzing the data going to be able to keep up with just the amount of data in terms of
mm,
the tools they have? But I'm certainly expecting
mm,
that our understanding will improve. The question to my mind is, as we get more data, or even from the dark energy survey, right now I said everything is consistent with the simplest picture where dark energy is just vacuum energy that is Einstein's cosmological constant. My dream would be, of course,
mm.
that we start seeing where it's not fitting that model, and we need to go to some other model of dark energy, uh, maybe
Mm.
involving quintessence, something else, maybe even a modification of gravity. That to me would be the most
Mm.
exciting, because it would really point us in a completely new direction in fundamental physics. But yeah,
Back to square one.
so we'll see.
So but you have to. but you have to complete it, Josh, before
That's right.
all the
Yeah, we only have
galaxies
about
fly away
50
beyond
billion
the
years.
horizon.
So that's right.
Funding is important. Excellent. Yeah. Thanks so much for spending time with me, Josh. This has been great, and good luck with
Well, thank you.
everything that
Those
you
are
do at
great
Fermi.
questions. It was an interesting discussion. Thank you. Bye-bye.
Thank you.